All right, welcome back everybody for today's session of the Cardiff Analysis Seminar in online format. So we are delighted to have Mariapia Palombaro from the University of L'Aquila, who will give a talk entitled Derivation of Linear Elasticity from Atomistic Energies with Multiple Wells. So thank you very much for accepting our invitation and for being here today. So over to you.
So thank you very much for inviting me. It's a pleasure to meet you, even though only virtually. So the results that I will present are the content of joint work in collaboration with Roberto Alicandro and Giuliano Lazzaroni from the University of Cassino and the University of Florence, respectively. So as the title suggests, the problem that we studied is the derivation of linearized energies from atomistic energies with multiple wells. So discrete energies that are minimized on the union of several wells. So let me start with a short introduction to linear elasticity and with a description of the variational approach that we follow. And for the moment, let's stick to the continuum setting. So assume we have a hyperelastic material that occupies the region omega of the space. Omega is a bounded domain in RD. If V is a deformation of the material, we assume that the stored energy of the hyperelastic material is given by this integral functional, where the density W defines, or better, its derivative, defines the stress tensor. As customary in these kinds of problem, one assumes frame invariance, which means that the energy does not depend on rotations of the system. And we also assume that the reference configuration is stress-free, which means that the identical deformation, whose gradient is the identity matrix, is an equilibrium of the system. Now, the derivation of linear elasticity is based on the observation that since the identical deformation is an equilibrium when no external load is applied, we expect that it's reasonable to expect that small external loads will produce small displacements. So within the theory of continuum mechanics, a possible approach, a variational approach to the derivation of linearized models from nonlinear models consists in studying minimum problems for a suitably rescaling of this energy when the deformation is close, is a small perturbation of the identical deformation. In general, a small perturbation of an equilibrium that we can always assume to be the identical deformation. So this is the approach that we follow. So we are interested in the minimizers of suitable scaling of this energy. And we would like to say that the linearized energy is a good approximation of this. So we introduce a small parameter epsilon. We consider an external load, a small load of size epsilon, so epsilon L. And we write the deformation V as the sum of the identical deformation plus the displacement epsilon U. Then the total energy, written as a function of U, of the displacement U, is the sum of the stored energy and the external load. Let me show you now a formal derivation of the linear elastic energy associated with U. Just a formal derivation. So assuming that the identical deformation is an equilibrium, and assuming some regularity, a C2 regularity is enough, in a neighborhood of the rotations, we can tailor expand the energy with respect to epsilon, about epsilon equal to 0. So in this way, we can approximate the density of the energy by a quadratic function plus a small error. And if the gradient of u of the displacement is bounded, replacing f by u, by the gradient of u, by dividing the total energy by epsilon squared and taking the limit as epsilon goes to zero, we obtain this limit energy. So we recognize here the quadratic linear energy that acts on the gradient of u, but in fact on its symmetric part. By frame invariance, one can see that this functional only depends on the symmetric part of the gradient. So the linear elastic energy associated with the displacement u is given by this quadratic functional that we all know, right? However, this is just a formal computation. This computation does not guarantee the convergence of minimum problems, does not guarantee that the minimizers or almost minimizers of this functional will converge to the minimizer of this functional under suitably boundary condition, of course. And moreover, we also assume that the gradient of u of the displacement is bounded, which is not always the case. So this is just a formal computation, and the first rigorous justification of this procedure was done by Dalmaso, Negri, and Percivale in 2002. So in their result, they work with potentials that are minimized only on one well, which is the set of rotations. And the density of the energy is assumed to grow quadratically away from the set of the rotations, okay? And it vanishes only in the rotations, at the set of rotations. Then some regularity is assumed in the neighborhood of the rotations. Of course, when we study minimum problems, we need to assign some boundary conditions. So the boundary condition is assigned on the displacement. U is equal to G on a portion of the boundary of omega or on the whole boundary. This is the rescaled functional. What they proved, Dalmaso, Negri, and Percivale, is the following gamma convergence result. So what does it mean? The first line is called compactness. Compactness property of sequences of displacements with equibounded energy. So if I have a sequence U epsilon with equibounded energy, so the energy stays bounded along the sequence of displacements, then U epsilon is bounded in H1. Okay, so this is very important. The second line says that this sequence of functionals, of rescaled functionals, E epsilon, gamma converges to the quadratic energy. Now, what gamma convergence is not important. It's a variational convergence that, together with this first condition, the compactness, ensures that this limit is a good approximation of this sequence of functionals. So these two properties together implies that the sequence of minimizers will converge to the minimizer of the elastic energy. So this is the result, and the result is valid for one well potentials only. And this result appeared quite late, only in 2002, because until that time, this compactness property was missing. So the gamma convergence was not the heartbeat. What was missing until then was this compactness property. So to prove that sequences with equibounded energy are compact. And, but at that time, the rigidity estimate of Heuristic, James, and Müller appeared. And this rigidity estimate turns out to be the key tool to prove compactness. So you may be familiar with this, but if you are not, it's not important. The rigidity estimate of Heuristic, James, and Müller says that if the gradient of a Sobolev function is close to the set of rotations in some LP, then the gradient must be close to a constant rotation. So this is a quantitative version of the Liouville theorem. Okay, so this gradient cannot be close to the rotations without being close to a constant one. Okay, so let me show you how this estimate enters the compactness properties of the gradient of the displacement. So let's write V epsilon, which is the deformation, as the identical deformation plus the displacement. We want to prove the compactness of U epsilon, okay? By assumption, the energy, E epsilon, is bounded from below by the square distance from the set of rotations. So this inequality follows from the assumption. The rigidity estimate of Frieseke, James, and Müller implies this inequality. So says that if we are close to the set of rotations, then the gradient of the deformation, V epsilon, is close to a constant matrix. So we get a sequence of matrices of rotations R epsilon. But then using the Dirichlet boundary conditions, which says that V epsilon is equal to X plus epsilon G, where G is given and does not depend on epsilon, one can prove that this sequence of rotations is in fact close to the identical matrix. So here it's important to use the Dirichlet boundary conditions, because it's this that will select the rotation. So we are close to the identical matrix, the identity matrix, and by writing the gradient of the epsilon as the identity matrix plus epsilon gradient of U epsilon, we get this. So compactness follows straight away. So the rigidity estimate turned out to be a crucial tool in the proof of compactness. Notice that here it's essential that the energy is bounded from below by the distance from the set of rotations. In the case when the energy is minimized on more than one wells, so on the union of several wells, here we will see that here we will have the union of these wells, and this rigidity does not apply. At least it's one cannot directly apply this rigidity estimate. So the difficulty in the case of more than one well will be due to the presence of several wells and to the fact that this rigidity cannot be applied directly. Okay. Okay. So later, several extensions of this result appeared, always in the case of one well energies. So the first extension, due to Agostiniani, Dalmaso, and De Simone, deals with the densities that satisfy mixed growth assumptions. So are bounded from below by the minimum between the square distance from the set of rotation and the p distance from the set of rotations, where p can be also less than 2. And this kind of growth arises now naturally in various applications, for example, when there are dislocations. In presence of dislocations, which are defects of the materials, the gradient of the deformation is not in L2, and then one has to work with densities that grow slower than quadratic when close to the dislocation. Okay, so in this case, of course, compactness will hold in W1P if P is less than 2. And then another extension of the linearization result is due to Schmidt and Agostiniani plus Koumatos. And in their work, there is always this mixed growth condition, and the energy is minimized on the union of two wells. The first well is the set of rotations, And the second well is a small perturbation of the set of rotations. So the distance between these two wells is very small, of order epsilon, which is the order of the size of the load. Okay. So essentially, until this time, linearization was proved only for one well energies. Okay, the problem that we wanted to study is to generalize this, so to obtain linear elasticity for energies that are minimized on the union of several wells whose mutual distance is fixed and is of order 1. So we consider several wells that are of this form, rotations times ui. We assume that the first is the set of rotations, so U1 is the identity. We want to allow for this mixed growth assumptions. So the density of the energy is bounded from below by the minimum between the square distance and the p distance. Now, as I already pointed out, the issue here, when there is more than one well, is the compactness. If one assumes that the wells are strongly incompatible, which means that one cannot have gradients close to several wells at the same time, close to several wells in sets of positive measures. So if this is not possible, if the wells are strongly incompatible, then the rigidity estimate by Chaduri-Müller says that the distance, the L2 norm of the distance of the gradient from the union of the wells is bounded from below by the distance from a single matrix, which is a matrix belonging to one of these wells, okay? But this is a very special case, the case of strongly incompatible wells. If this assumption is not made, then we cannot expect compactness. So in general, there is lack of compactness for the displacement. And here there is a simple counterexample that one can construct. So K is the union of these two wells, the rotations, and rotations times U, where U is the identity matrix plus a rank 1 matrix. This means that one can laminate, one can define a deformation V whose gradient lies in both wells on in sets of positive measures. So the gradient of V is the identity in half of the domain and is equal to U in the other half of the domain. The energy, of course, is 0 along this sequence, but the gradient of the displacement, which is this, is of order 1 over epsilon, and therefore the gradient of U epsilon cannot be in LP for every P, for any P. The LP norm of the gradient of U epsilon diverges as epsilon goes to 0, right? So in general, unless strong incompatibility assumptions are made, we cannot expect compactness. So how can we recover compactness, which is an essential, a very important property in order to guarantee that the linearized model is a good approximation of the nonlinear energy? An idea that we successfully exploited in the continuum setting is to introduce a singular perturbation that penalizes transitions between the wells. So we add to the energy a term that prevents too many oscillations of the gradient. So this was our energy before rescaling. We add to the energy a term that depends on second derivatives. Of course, second derivatives will prevent too many jumps of the gradient from one well to another. Of course, we don't want that this term appears in the limit, so we multiply it by eta, and we will take the limit eta that goes to 0. So we express the energy in terms of the displacement and we rescale. And the task now is to find a suitable scaling of eta with respect to epsilon, so that in the limit we obtain a linearized energy where there is not a remainder of this term. So eta should be big enough in order to prevent too many jumps of the gradient, but small enough as to disappear in the limit. Okay. And so this is the program that we followed in the continuum setting. And together with Alicandro, Dalmaso, and Lazzaroni, we proved the following result. So if eta satisfies these assumptions, this scaling assumption with respect to epsilon, so in dimension 2 is much larger than epsilon, and in dimension d larger than 2, it satisfies this inequality. Then we can prove compactness, the compactness of the displacements, the sequence of the displacement, and gamma convergence. And as I said, these two properties together ensures, guarantees the convergence of minimum problems. And if, in fact, we proved much more than this, if we require compactness in W1R for R less than 2, we can also enlarge the range of eta. And we also prove that this scaling is optimal. Okay, so under this assumption, we can derive the linearized functional and prove compactness. As I already pointed out, the issue here is the compactness. So in order to have compactness, one cannot apply directly the rigidity estimate of Friesiger, James, and Mueller, but one has to first prove a one-well lower bound on the energy. So one has to prove that this energy is bounded from below by the distance from only one well. So most of the work is here in this compactness proof. Now, let's come to the discrete setting. So in the continuum setting, we said that we added a singular term to the energy that penalizes transitions of the gradients from one well to another. In the discrete setting, we will see that this penalization role is played by interactions beyond nearest neighbors. So I'm not assuming that we are all familiar with atomistic energies or discrete systems. So I will try to say things in the simplest possible way. So let's start from this very simple situation. Think of the two-dimensional setting. We have a discrete system, a system of atoms sitting on a lattice. Assume we have this triangular lattice, where the distance between the atoms is eta, okay? We consider the portion of the lattice that lies inside a domain omega, a bounded domain omega. So eta is the atomic distance, interatomic distance. Assume that the energy, the discrete energy, is a pairwise energy of this form. So it's the sum over all pairs, interacting pairs of energies that depend on the distance of the atoms in the deformed configuration. So V is the discrete deformation and is defined on each atom. And for the moment, think of these pairwise interactions where the energy depends only on the distance between the atoms in the deformed configuration. By rescaling, one can rewrite this energy in this form, so in terms of the discrete gradient. And this factor here, eta to the d, denotes a bulk scaling. So this is an analog of a discrete analog of a volume integral, okay? Of course, this energy is frame invariant because it only depends on the distance between these pairs of atoms. For this class of energies, Alicandro and Cicalese proved an integral representation result. So they proved that under suitable growth and decay assumptions on the potentials G eta, this sequence of functionals as eta goes to 0 is well approximated by a continuum limit of this form. So an integral function with density W. So of course, in principle, we could first perform a discrete to continuum limit as they did. And then we could perform a linearization. So we first obtain an integral functional of this form, and then we could linearize this integral. However, this cannot be possible, cannot be done in the case of two or more wells. In the case of one well, this is possible, but in the presence of two or more wells, what happens in the passage from the discrete to the continuum is that one can mix gradients lying in different wells at a negligible cost. And this results in a W, in a density of energy, W, that has too many minimizers. So instead, these oscillations are forbidden in the linearization regime. Recall that I recall that in the linearization regime, we are dividing the energy by epsilon squared. So these oscillations are forbidden. So what we need to do instead is to perform a simultaneous limit. So a discrete to continuum analysis and a linearization at the same time. So we need to find a suitable scaling of eta with respect to epsilon so that one can obtain a linearized energy from this scaled discrete energy. So as a byproduct of our results, we prove that the discrete to continuum limit and the linearization do not commute in the case of two or more wells, while they do commute in the case of only one well. So if there is only one well, one can first perform a discrete to continuum limit and then linearize the resulting energy. But here it's not possible, okay? Well, let me tell you what were the available results in the discrete setting before our results. So the available results only concerned the one well case and a very special class of discrete energies. So there was a paper by Briders, Solce and Vitali, where only interactions between nearest neighbors are considered, and the energy is minimized on the set of rotation. So in their case, the rigidity estimate applies straight away. And then there was a work by Schmidt, where he considers very short range interactions, possibly not individually equilibrated in the reference lattice. I will give you more details about these two papers in the next few slides. So the one well case and very special class of discrete energies. So our goal was to extend the analysis to the multi-well case and to a large class, a broader class of discrete energies. Let me show you the result by Briders, Solce and Vitali, which is the first in the discrete setting. So in their model case, we have harmonic springs connecting nearest neighbor atoms. So each atom interacts with the 6 surrounding neighbors, okay? We have a harmonic springs, and the energy here is the sum over Xi, where Xi is the set of the 6 directions, okay? And here we have the sum over neighboring atoms, okay? So X and then X plus eta Xi. X plus eta Xi are these 6 surrounding neighbors, okay? Okay, in Braid's Solci Vitali, the non-interpenetration assumption is assumed. Oops. So they assume that the gradient of a piecewise affine interpolation of the discrete deformation with respect to the triangulation of the lattice is positive. So satisfies this positive determinant constraint. This means that reflections are not allowed. So the only ground states are the rotations, okay? The energy is minimized only on the set of rotations. And because of this, one can prove straight away that the energy is bounded from below by this, the square distance from the set of rotations. So I repeat that the gradient of V here is the gradient of continuum interpolation of the discrete deformation, okay? So in their case, the compactness is not an issue. And what they prove is that imposing boundary conditions for the displacement and after rescaling the energy, they prove that the energy gamma converges to a continuum limit, which is an integral functional with density phi1, and they give you a formula for phi1. Phi1 is given by this. So this keeps track of the discrete nature of the problem. This is the sum over the 6 directions of this quantity. And this functional, of course, only depends on the symmetric part of F, so of the gradient. Okay, so this is the result. And the density phi1 can be obtained in the beginning. So before proving the gamma convergence, one can identify phi1 in the same way we did in the beginning with the formal computation. One can evaluate the energy for U equal an affine map. So we compute E eta epsilon at U equal Fx, and then one can Taylor expand about epsilon equal to 0. This would give the following approximation of the discrete energy, where phi1 is precisely this, so the density that will appear in the limit. And this can always be done also in our more general setting. The way we identify the density is in this way. So we first perform a formal computation by Taylor expanding, and then we prove a rigorous result. Okay. Okay, so this was the first derivation of linear elasticity from a discrete energy minimized on a single well with the non-interpenetration assumption. So the determinant is positive. We can add some complexity to this case and obtain now a two-well energy by dropping the non-interpenetration assumption. So the first model that we studied with an energy minimized on the union of two wells is obtained by taking the Braid's Solci Vitali model, so the harmonic springs, and dropping the positive determinant constraint. So if now reflections are allowed, which means that this kind of deformations are allowed, we can change the orientation of the triangles in the deformed configuration. This means that the energy will be minimized on the rotations and on the set of reflections, right? However, if we only take into account nearest neighbors, we cannot have compactness. So in order to have compactness and in order to prevent too many folding of the lattice, we need to incorporate into the energy the effects of nearest neighbor interactions. So here, the sum runs over nearest neighbor directions, which is B1, and B2 is the set of next to nearest neighbor directions. So each atom now interacts with the 6 surrounding nearest neighbors and the second neighbors, which are these diagonals, these long diagonals. Okay, so there is another one here, up here, another one here. So 6 plus 6. So this is the first case. So it's a simple model, and it's the first two-well energy, discrete two-well energy that we considered. Okay, so for this energy, by imposing a boundary condition, one can prove the linearization. So under this scaling of eta with respect to epsilon, one can prove compactness and gamma convergence. And here the density of the energy is this one, which is very similar to phi1, the density appearing in brightest Solci Vitali. The difference is that here this sum runs over the union of two sets, the directions of the nearest neighbors and the other 6 directions of the next two nearest neighbors. Okay. Okay, so this is the first case that we studied of a discrete energy with two wells. Okay, and what we learned from this simple example is that if we want to have compactness, we need to incorporate into the energy the effects of the interactions beyond nearest neighbors. Okay, so long-range interactions. Let's come now to the general model. So in our general model, we can have any Bravais lattice in any dimension. And by a change of variable, we can always assume that the Bravais lattice is the cubic lattice. So it's ZD. Eta ZD, of course. So eta is the lattice spacing and eta is the reference configuration, which is the portion of the Bravais lattice lying inside a bounded domain omega. And V is the discrete deformation. Now let's fix an integer m. M can be any integer, okay? Even very big. We consider a discrete cell, which is this cube, 0m to the d, intersected with the lattice. So it's the set of atoms inside this reference cell of side m. We assume, so in the general model, the energy can be decomposed as a sum of two terms, a bulk term and a surface term. The bulk term is a cell energy. What does it mean? It's the sum over all cells, discrete cells contained in the lattice of a density of a potential W cell that is a function of the discrete gradient. So here we have all the finite differences contained in the cell. So I fix x. X is this. Then in this picture, m, the integer m is 3. Okay, so x plus eta cm is this. Is the set of points inside this red square. I consider all the interactions within this cell. So I consider the finite differences. W cell is a function of all these finite differences. Okay, so nabla prime here denotes the discrete gradient. And the surface term accounts for interactions that are close to the boundary. Of course, this is a discrete boundary, okay? But let's not bother about this term. Okay, so in our general model, we consider cell energies. So energies that are functions of finite differences within a cell, which can be arbitrarily large. Okay. The case m equal to 1 is the case considered in Schmidt. Okay, so Schmidt considers a cell energy where m is 1. So the cell is very small. It's just a square of side 1. Okay, of course, then we rescale it. It's side eta. Okay, and there is only one well in this case. While in our case, m can be arbitrarily large but finite. Okay. Well, so an example of interactions of energies covered by our analysis are the pairwise energies, so energies that depends on the distance between pairs of atoms. This class of energies falls into this framework. Every pairwise energy with finite range interaction, so G here is compactly supported, is zero outside the ball, can be rewritten as a cell energy. So every pairwise energy can be written as a cell energy. And this is possible by suitably introducing these weights in front of the energy of each single interaction. And this is because, you see, if I'm considering this interaction will be counted several times. Once in the red square, when I look at the interaction within the red square, and then it will appear again when I compute the interactions within the blue cell. And this is because the same interaction is contained in several cells. So in order not to count it too many times, we introduce these weights. So by suitably defining these weights, one can rewrite every pairwise energy with finite range interactions as a cell energy. Okay. Well, what are the assumptions that we require on W cell? So this is the list of our assumptions. We assume that W cell is frame invariant, okay, when the energy does not depend on rotations of the system. We assume that W cell is minimized on the union of several wells. So we have L wells, okay? So W cell is zero if and only if the deformation is an affine map with gradient that belongs to K. And K is the union of L wells. L can be an arbitrary number, and there is no assumption on the matrix, on the matrices UI, okay? We assume some rigidity, a coercivity condition, which says that the energy of a cell within a cell is bounded from below by this integral. Here, the gradient of V is the gradient of a continuous interpolation of V with respect to a triangulation of the lattice. Okay. So the energy of the cell is bounded from below by the integral of the minimum between the square distance and the p distance. And then we require this very important assumption. This is important for the compactness, and we want to penalize too many transitions. So we assume that if we have two neighboring simplices of the triangulation, where the gradient of the deformation is close to one well in one of these simplices and close to another well in the other simplex, then the energy must be positive. So it's bounded from below by a positive constant. So whenever the gradient is close to different wells or on neighboring simplices, we pay something, okay? And finally, we assume some C2 regularity of W cell in a neighborhood of the union of the wells, okay? So this is the set of our assumptions. And under these assumptions, we prove the linearization. So we give these general assumptions, and then we provide several examples that are covered by our analysis. And among our examples, there are the pairwise, every pairwise interaction with finite range, but we prove even other kind of examples. Okay, now let's come to the Dirichlet boundary condition. We assign a boundary condition on a portion of the boundary or even on the whole boundary. Now let's stick to the case of the whole boundary so that the surface term only depends on the boundary term, and so it can be neglected. So we can renormalize and scale the energy so that we are left only with this bulk term. Okay, so again, by taking U equal to an affine map and Taylor expanding the energy, we can identify the limiting density, the density that will appear in the linearized energy, which is given by the Hessian of W cell, okay, computed at the discrete gradient of the identity matrix. So this is our result. And so if W cell satisfies the set of our assumption, and eta satisfies this scaling, so we fix R, where R is larger than 1 and less than P. If eta satisfies this scaling, then we have compactness of the sequence of displacement in W1R, and we can also prove gamma convergence. These two together implies the convergence of minimizers. Okay. Okay, as I already said, the main technical difficulties are due to the multi-well structure, but this time also to the long-range interactions. So the multi-well structure of the energy poses difficulty for the compactness. We already observed this. So one has to first prove a one-well lower bound for the energy. While for the lower bound in the gamma convergence one has to prove an upper and a lower bound. Okay, the presence of these long-range interactions makes the proof of the lower bound non-trivial. Okay, so here we introduce a novel idea which is potentially which could be potentially used in other applications. Okay. So usually here, when one deals with discrete energies, what one usually does is to rewrite the discrete energy as the integral depending on the gradient of a continuum interpolation of the discrete deformation. In this case, this is not possible, because there are too many interactions. So it's not possible to define a continuous interpolation whose directional derivatives coincide with the finite differences. So one has to overcome this difficulty. And to do this, we introduce a new idea, which I cannot describe, but this is, let's say, the main part of the work. Okay, and in the case of pairwise energies, which are covered by our analysis, one can also explicitly compute the density, the limit density. And this is the explicit formula for phi, for the limit density, for a pairwise energy. And remark 3, we provide several examples of energies that satisfy our assumptions. And among our examples, there is this example, which is quite interesting because it displays what is called frustration. So in this example, we have harmonic springs. So this is a two-dimensional example. So here there's two, I forgot. So here these two, this is a two-dimensional example where the atoms are linked by harmonic springs. And one can prove that in a certain range of these constants of kxc and xc, our assumptions are satisfied, and the system is frustrated, which means that the individual interactions are not equilibrated in the minimal state. So the global minimizer is not a minimizer for each single interaction. Okay, so in this example, each atom interacts with the atom here, this atom, the central atom, interacts with the atoms that are connected by these colored lines. Okay, and in this example, m is equal to 2. The wells are given by the rotations and the reflections. Okay, so this is an example of a two-well energy that displays also what we call frustration. Okay, do I have time? No, I don't have time to give you also a heuristic argument for compactness. So sorry, I will skip it. And let me come to an overview of the discrete results. So in our work, we consider a general discrete model, which is based on cell energies. So energies that can be written as cell energies, energies accounting for interactions within cells, which can be arbitrarily large. We provide several examples. For example, also laminates, where the wells have positive determinant. But we may include also multi-body interactions with positive determinant constraint, but also negative determinant, as in the case of the reflections. Pairwise interactions are covered by our analysis, and in this case, we can explicitly compute the limiting energy, and we give an explicit formula for the limit energy. We exhibit examples where the minimal configuration displays frustration. Then I haven't discussed the loads, but of course we can incorporate non-zero loads to the energy. And finally, we can handle also the case of Dirichlet boundary conditions that are assigned only on a portion of the boundary. Okay, in my description, the Dirichlet boundary condition was assigned everywhere. In this way, we could remove the surface term from the energy and study only the asymptotic behavior of the bulk part. But we can handle also the case of Dirichlet boundary condition assigned on a subset of the boundary. And so this is what I wanted to say, and thank you for your attention.
Thank you very much. So, are there any questions for Mariapia? Nicholas.
Mariapia, could you please show and talk about a slide about a modica modular type energy that you skipped towards the end?
Okay, thank you. Thank you very much for your question, Nicholas. So here I want to give you a heuristic argument for compactness, which is here. So what is this heuristic argument? Our functional looks like a modica modular type energy with a curve-free constraint. So it's a functional which the sum of a term that would like the gradient to sit in these wells, and another term that penalizes this transition. Curve-free means that the variable is a gradient. Okay. Now, there are papers that proved upper and lower estimates for this energy. And this shows that this energy goes like this term here. So what does this mean? If we consider a sequence of with equibounded energy, one can prove that the limiting deformations have gradients in BV and takes values in the set of the wells, in the union of the wells. So one can prove that this energy goes like approximately eta times the HD-1 measure of the jump set of the limiting deformation gradient. This has been proved by Conti, Schweitzer, and W. Friedrich in the case of two wells, but with a rigorous analysis. But this scaling can be proved also for more than two wells. In the discrete setting, we have something similar. This is our discrete energies. And because of the third assumption, the penalization of the jumps from one well to another, one can prove, and this has been done in previous papers, that the discrete energy goes in the same way. So is approximately given by along sequences with equibounded energy, eta times the measure of the jump set of the deformation gradient. Now, in the linearization regime, we rescale the energy by epsilon squared. You remember the sequence that we studied was 1 over epsilon squared times these energies. So if we rescale, we see that the rescaled energy goes like this. Okay. Now, if omega epsilon is the set where the gradient of the deformation is not in the right well, which is the set of rotations, but is close to the other wells, okay? If we denote by omega epsilon, the bed set, let me call it the bed set, then one can see that in omega epsilon, the gradient of the displacement goes like 1 over epsilon. So because the distance between the wells is fixed, is of order 1. So if we want to have compactness in LR for some R, it would be useful to have an estimate on the measure of this set, an estimate of this form, that the measure of omega epsilon is less than epsilon to the power R, if we want compactness in LR. Well, now the boundedness of the energy here implies that the measure of this jump set, this is all approximate, okay, is bounded by this quantity, epsilon squared divided by epsilon. And by applying the isoperimetric inequality, we obtain that the minimum between these two measures, the measures of the bed set or of its complement, is bounded by this power of epsilon squared over eta. Now, if the boundary conditions are such that the minimum is attained by the measure of omega epsilon, if eta satisfies this scaling, one obtains this. And this gives the compactness of the gradient of U epsilon. Of course, this is only a heuristic argument, but the main idea, the essential idea is here. Okay, both for the continuum and for the discrete. Okay.
Are there any further questions?
Hi, I have a question. Thank you for the talk. And it's probably a more general question, not about multi-well problem, but when you have this, these models that derive linearized elasticity, continuum elasticity from discrete settings. So what is the compactness argument there? Because in continuum setting, in continuous setting, you use the rigidity theorem. So is there an analog of this in the discrete setting?
Yeah, we need to prove a one-well lower bound, which says that the distance from K, which is the union of this no, more precisely, we need to prove that the energy is bounded from below by the distance from only one of these wells. Okay, this is what we need to prove, and this is this heuristic argument that I showed. It's this. This proves that in this case that the energy is bounded by the distance from the set of rotations. Okay.
Yeah, I understood this. My question was, the next step was to use the rigidity estimate, isn't it?
No, the rigidity estimate cannot be applied directly. Okay, because
yeah, what is the analog of this in the discrete?
No, there is not an analog. You first prove a lower bound. So you first prove that your energy is bounded from below by the distance from only one well, and then you apply the rigidity estimate. Once you have only one well, you apply the rigidity estimate that gives you constant rotation, which will be then close to the identity.
But you're in discrete setting, and the rigidity estimate is available in continuous setting, isn't it?
Yes, but we work with piecewise affine continuous.
You just use triangulation and yes. This works like very, it's so straightforward, right? There is nothing to invent. You just take your discrete set of discrete setting and make it continuous with triangulation thing, right?
Yes, in the compactness argument, it's simple to use the continuous representation for the discrete energy.
Yeah, that was my question essentially.
In the gamma limit, in the gamma convergence, this is difficult. But for the compactness, yes, you use the piecewise affine interpolation. We use the Kuhn decomposition. We divide each cube into simplices, and we consider the piecewise affine interpolation. Yeah.
I see. I see. Thank you very much. Yeah, it was. This was my question actually. Yeah.
Okay. Thank you.
Thank you.
So more questions? So perhaps, Nicholas, yeah, please go ahead.
You're muted, Nicholas.
Maybe it's maybe a bit naive question, but I was wondering whether there's any kind of scaling where, like in the original Modica modular case, you can see in the limit linear elasticity in the bulk plus surface energy on areas separating where you're close to one of the, say, two wells.
This has been done in some recent work by Elisa Davoli and Manuel Friedrich. Yes.
From a continuum
No,
model or from a
in the
discrete?
continuum setting, not in the discrete. In the continuum setting, this has been done by these two guys, Davoli and Friedrich, yeah, where they combine this modica mortola with the linearization. And so you get both these terms, the linear elasticity and this interface term, interfacial terms. Yes.
Thank you.
And there is also this big bulk of work on those lattice, what is it, the crystal lattices, where you have both, so where they achieve different wells, right? The different minimas, and they call Martin-side.
Yes, laminates. Yes,
laminates. So
yeah, laminates also are covered by our analysis, and we provide examples of laminates where, yeah, you can have gradients with positive determinant lying on wells. Yes.
But essentially, introducing this penalization and choosing the right eta removes this, so completely removes this possibility of
too many. Well, the presence of this penalization prevents too many oscillations, too many jumps. Yeah. So, but in the discrete setting, it's the interaction, taking into account interactions beyond nearest neighbors prevents this, okay?
Yes, yes.
Not that we add further terms. We incorporate the effect of long-range interactions, and this, the presence of these bonds prevent the appearance of too many jumps from one well to another. This.
Yeah.
If we don't include, we only stick to the nearest neighbors, then we cannot expect compactness.
Thank you.
You're welcome.
All right, so maybe I'll have a final very quick question. So it's very basic. I'm not an expert in this area. So if may you go please to slide 8. So
here?
Yes. So in the theorem, so you essentially have two very different behaviors, right? When dimension is 2, eta has to be much larger than epsilon. And when the dimension is greater than or equal to, strictly greater than 2, then eta can be, okay, of the same order as epsilon, okay, up to a power depending on dimension. Is there an intuitive reason for this different behavior, or?
It's like this, and we also prove optimality. It's not just a technical assumption. We provide examples where we violate this and we don't have compactness.
So it's not something technical that's happening.
No, it's not technical. These are optimal. This scaling is optimal. I haven't written, maybe I don't remember if I said that, but and here in the most general statement that we give, so in compactness in W1R, if we want compactness in W1R, the range for eta will depend also on R, and the scaling that depends also on R is optimal. And also in the discrete setting, we provide some examples where the scaling is optimal.
And here much bigger, I suppose it means that epsilon over eta goes to 0.
Goes to infinity. Epsilon over eta, yes, goes to 0. Yeah.
Yes.
Yeah.
I see. Okay. Yeah. Thank you very much. Any more questions? So if that's not the case, so before thanking the speaker again, I just remind everybody that next week we go back to in person, of course, streamed for people who are unable to attend. So we will have Uzis Milansky here in Cardiff. So, and now let's thank the speaker again for the very nice talk. So.
Thank you.